In this video, I introduce more details about generative adversarial models. Here is the architecture of a GAN model that includes two neural networks. One is a generator G, one is a discriminator D. The generator is trained to generate an image from a uniform noise distribution, while discriminator is used to predict the input from a real image or from a generative model. The generator is trained to improve the quality of the generated image until the discriminator cannot tell the difference of the input X from a real image or from a generative model. GAN is a two-player minimum maximum game. Generator and the discriminator fight each other until reach the Nash equilibrium. The two-player game plays out in two scenarios. In the first scenario, training examples X are randomly sampled from a training dataset and used as input to the discriminator. The goal of a discriminator is to predict the probability that input is real rather than fake, namely dx1 for all data X. In the second scenario, input Z to the generator are randomly sampled from models prior over the latent variables. The discriminator receives the input GZ, that is a fake sample created by the generator. In this scenario, the discriminator strives to make DG approach 0, while the generator strives to make DG approach 1. Nash equilibrium corresponding to D equals 1/2 for all X from the data and the model. The cross entropy is defined as a cost function used for the discriminator by two expectations, which is trained to maximize GD as the binary classifier to predict a probability distribution of a P model in P data. The discriminator is trained on two mini batches, one from the real dataset, where the label is 1 for all examples, and one from the generator, where the label is 0 for all examples. By training the discriminator, we obtain a ratio P data divided by P data plus P model. Generator is trained to maximize the maximum of cost function with respect to theta D to make this P model close to P data until reach the Nash equilibrium. In practice, again, minimize GIS divergence between the data and the model distributions and converges to the Nash equilibrium because GIS divergence is symmetric. Namely, we can switch order of PD and P model. GIS has the same value. For more details, please check with this reference. Thank you. Bye.